photograph of a galaxy can give the wrong impression. In an image, everything seems settled. A bright center holds its place. Spiral arms curve outward with patient symmetry. Dust lanes cross the starlight. Nothing appears to move. Even a galaxy caught in the middle of an encounter can look suspended, as if gravity had arranged the scene and then left it untouched. But the stillness belongs to the photograph, not to the galaxy. Every star is moving. Gas is falling, cooling, heating, and being pushed back out. Smaller systems are being pulled apart in the outskirts. New stars are forming in dense clouds, while older stars shed material into the space between them. Far beyond the visible glow, an extended dark matter halo participates in a much larger gravitational structure that reaches into the surrounding universe. A galaxy is not a finished object. It is a process that can last for billions of years. That process has no clean beginning in the way a single star does. There is no first instant when a complete spiral galaxy suddenly appears. Galaxies assemble gradually. Matter collects inside growing gravitational wells. Gas settles into denser regions. Stars begin to form. Fresh material arrives from outside. Smaller galaxies are captured. Large galaxies pass near one another, distort one another, and sometimes combine. Even the shapes we recognize are temporary arrangements. A disk can thicken. A bar can form across the center. Spiral structure can strengthen, weaken, or change. A collision can scatter stars onto new orbits. A galaxy rich in cold gas can spend long period producing stars, then enter an era when that activity declines. And decline does not mean disappearance. When astronomers describe a galaxy as quenched or passive, its stars may still be shining in enormous numbers. What has changed is the supply of cold, dense gas able to collapse into new stars. The galaxy remains gravitationally bound. Its stars continue their orbits. Its central black hole may remain. Its halo remains. What fades is one particular form of activity, the steady creation of new suns. So the life of a galaxy is less like the life of an animal and more like the history of a landscape. A coastline can be shaped by processes that began long before any observer arrived. Rivers shift, sediment moves, mountains rise and wear down. The shape seen at one moment is real, but it is not permanent. A galaxy is similar in that sense. Its present form contains traces of earlier events, while forces already at work are preparing whatever comes next. Tonight, we will follow those forces across cosmic time. We will move from the nearly smooth young universe into the first growing structures. We will see how dark matter helped provide gravitational foundations before galaxies became luminous, how ordinary gas found its way into those structures, and how the first generations of stars changed the chemistry of space. Then the view will widen. Galaxies will draw material from their surroundings, build disks, rearrange their interiors, and exchange matter with the halos around them. Some will grow through repeated encounters. Some will absorb smaller companions so completely that only faint stellar streams remain as evidence. Some will be reshaped by crowded environments, while others will change from within, and eventually we will arrive at the long fading of star formation, when a galaxy can remain full of light while becoming less capable of making anything new. Across all of this, one idea will stay with us. A galaxy survives not by remaining the same, but by continuing to change. The story becomes clearer when the visible galaxies are removed from the picture. Imagine the universe before there were spiral arms, star clusters, glowing nebulae, or even the first generation of stars. Matter already existed, space was already expanding, and gravity was already at work. But on the largest scales, the young universe was remarkably even. There were no mature islands of light separated by deep cosmic emptiness. There were only very small differences from one region to another. Those differences were enough. A place containing slightly more matter than average exerted slightly more gravitational pull. That advantage was tiny, but gravity had time. Matter moved a little more easily toward the denser region. The region became denser still, and its pull grew stronger. Elsewhere, places that began with a slight shortage of matter gradually became less populated by comparison. Over immense spans of time, this simple imbalance became one of the most important patterns in cosmic history. We can still observe a record of those early variations in the cosmic microwave background, the oldest light that can travel freely to us from the early universe. It comes from an era about 380,000 years after the Big Bang, when the cosmos had cooled enough for electrons and atomic nuclei to combine into mostly neutral atoms. Before then, free electrons scattered photons repeatedly, making the universe opaque in much the same way that light struggles to cross dense fog. Once neutral atoms became common, many photons could travel far more freely. That radiation has been crossing space ever since. As the universe expanded, the wavelength of the light stretched with it, shifting into the microwave part of the spectrum. Today, instruments map this faint radiation across the entire sky. Beginning with COBE and later with WMAP and the Planck mission, astronomers measured its subtle variations with increasing precision. Each generation of observations added detail to the same early portrait, revealing a universe that was remarkably uniform but not perfectly so. The map is not perfectly uniform. Its temperature varies by only tiny amounts, roughly at the level of a few parts in 100,000. Those slight variations carry information about density, motion, and pressure in the young universe. They are not photographs of infant galaxies. Galaxies did not yet exist, but they reveal the uneven starting conditions from which later structure could grow. This is one of the quieter surprises of cosmology. The universe did not need to begin with enormous clumps in order to make enormous structures later. Small irregularities were enough if gravity was given sufficient time. The origin of those irregularities reaches into physics that is still being tested and refined. A leading framework is cosmic inflation, which proposes that the very early universe passed through a brief period of rapid expansion. In that picture, microscopic fluctuations present at extremely small scales could have been stretched across much larger distances. Those fluctuations would then become part of the initial pattern from which matter later gathered. Inflation has strong support as a useful framework for explaining several features of the observable universe. But physicists do not yet have a complete confirmed description of the mechanism behind it. The details remain an active area of research. For the story of galaxy formation, what matters is that the early cosmos contained measurable variations, and gravity could amplify them. Ordinary matter, however, was not working alone. Hydrogen and helium would eventually make stars, gas clouds, planets, and nearly everything we can see in a galaxy. But in the early universe, ordinary matter spent a long time interacting strongly with radiation. That made it difficult for normal gas to begin collapsing as efficiently as it would later. Dark matter behaved differently. Whatever dark matter is made of, it does not appear to interact with light in the ordinary way. It does not shine, and it does not cool into luminous clouds as normal gas can, yet its gravity is measurable. Long before the first stars appeared, concentrations of dark matter could begin growing around the slightly denser regions already present in the young universe. This gave structure a head start. The growth was not like a single cloud shrinking smoothly into one object. Smaller dark matter concentrations formed, merged, and became parts of larger concentrations. Across time, gravity built a network rather than a random scattering of isolated spheres. That network is the cosmic web. Matter became concentrated along long filaments and sheets, with denser intersections, forming where several structures met. Between them, lower density regions expanded into cosmic voids. The pattern stretched across distances far larger than individual galaxies. A modern map of galaxies still carries this architecture. Galaxies tend to gather along filaments. Groups and clusters often appear near dense nodes. Voids occupy much of the volume between them. The visible universe we recognize is therefore arranged in part by a structure whose foundations were established before any star had begun to burn. Within the web, growing dark matter halos created gravitational wells. Ordinary gas could fall toward them. As hydrogen and helium accumulated, the gas became denser. Unlike dark matter, gas could collide with itself. It could heat. It could radiate energy away. It could eventually slow enough for gravity to gather it into still denser regions. This difference between dark matter and ordinary matter helped determine the layered structure of galaxies. Dark matter remained broadly distributed through large halos. Gas could sink deeper, lose energy, and later form compact luminous systems inside those halos. The galaxy we eventually see is therefore only the bright inner expression of a much larger gravitational environment. Even today, a spiral galaxy may appear to end where its visible disk fades from view. The dark matter halo extends far beyond that boundary. For someone resting beneath a night sky, none of this structure is visible directly. The eye receives stars, perhaps a pale band of the Milky Way, and the dark spaces between them. Yet on scales far beyond human sight, those points of light occupy a web shaped by gravity across billions of years. The pattern was already beginning before there was anything in the universe that could look back at it. And inside the densest of those early gravitational wells, ordinary gas was approaching its next transition. It was becoming compact enough and cool enough for the first stars to form. The first light did not arrive all at once. Inside the growing dark matter halos of the young universe, ordinary gas was becoming denser. Most of it was hydrogen, with helium making up much of the rest and only tiny traces of a few other light elements. There was no carbon-rich dust, no oxygen-bearing chemistry, and none of the heavy elements that later generations of stars would scatter through space. That made cooling difficult. For gravity to compress a cloud into a star, the gas has to lose enough energy for pressure to stop resisting collapse. In the modern universe, many atoms, molecules, and dust grains help with that process. The first star-forming clouds had far fewer options. One of the important coolants was molecular hydrogen, which could form in small amounts even in this chemically simple environment. Where the conditions were right, that modest cooling was enough. Gas contracted deeper into a halo. Density increased. Small regions became self-gravitating. And sometime within the first few 100 million years of cosmic history, the universe crossed a threshold it had never crossed before. Nuclear fusion began inside the first stars. Astronomers call this first stellar generation. Population 3, the name comes from a classification system created long after the stars themselves were gone. Population 1 includes comparatively metal-rich stars such as the Sun. Population 2 refers broadly to older stars with lower abundances of elements heavier than helium. Population 3 is the label reserved for the metal-free or nearly metal-free stars that should have formed before earlier generations had enriched the universe. Their existence is strongly motivated by the chemical history we can observe, but their detailed properties remain uncertain. Simulations often produce first stars that are more massive, on average, than stars forming in places like the Milky Way today. Primordial gas cools and fragments differently from gas containing heavier elements and dust, but the first stellar population was probably not represented by one single mass or one simple kind of star. Different environments may have produced a range of outcomes. That uncertainty matters because the masses of those stars determined what happened next. A massive star can pour ultraviolet radiation into its surroundings. It can heat nearby gas, ionize atoms, and alter the chemistry of the cloud from which it formed. If the star is massive enough, its life is brief on cosmic scales. The core changes rapidly as fusion builds heavier nuclei, and the star may eventually die in an energetic explosion or collapse to a black hole. For the young universe, these deaths were a beginning. The Big Bang produced hydrogen and helium, along with small amounts of a few light nuclei, but it did not create the full chemical inventory found in later galaxies. Carbon, oxygen, silicon, iron, and many other elements were built through stellar processes and then returned to space through stellar winds, explosions, and other forms of mass loss. The first generations of stars therefore changed the raw material available to the next generations. A cloud that began almost entirely as hydrogen and helium could be enriched by the remains of nearby stars. Even a small amount of heavier material could change how the gas cooled. As enrichment continued, clouds could fragment in new ways, making it easier for lower mass stars to form. Dust eventually became another participant in cooling and chemistry. The transition was probably uneven. One halo could already contain material touched by earlier supernovae, while another, separated by a large distance, remained chemically primitive. Enrichment spread through expanding bubbles and outflows, rather than appearing everywhere at once. For a long interval, pockets of nearly pristine gas could exist beside regions where a previous generation of stars had already altered the chemistry. The early universe was becoming chemically layered as well as gravitationally structured. Galaxy formation had now become a feedback process. Gravity brought gas inward. Stars formed from that gas. The stars then returned radiation, energy, momentum, and newly made elements to their surroundings. Some gas was compressed, some was heated, some was expelled from the shallow gravitational wells of small early galaxies. Later, some of that material could fall back. The first galaxies were shaped by this exchange from the beginning. They were not miniature versions of the grand spiral systems we see nearby. They were compact, irregular, rapidly changing collections of stars and gas inside growing halos. Their internal structures were disturbed by star formation, infalling material, and frequent mergers with other small systems. Many would not survive as independent objects. A young galaxy could merge with another and become part of something larger. A smaller system could be pulled apart. Gas arriving along the cosmic web could change the direction of rotation or fuel another round of star formation. The identity of a galaxy at this stage was not fixed. It was continually being rebuilt, and while galaxies were changing themselves, their light was beginning to change the space between them. After the cosmic microwave background was released, most hydrogen in intergalactic space became neutral. Later, energetic ultraviolet photons began removing electrons from hydrogen atoms again. This long transformation is called cosmic reionization. It did not happen from one location or at one moment. Ionized regions grew around sources of energetic radiation. Over time, those regions expanded and overlapped until most intergalactic hydrogen had been reionized. The broad picture is well established, but astronomers are still working out exactly which sources supplied tide, how much of the required radiation, and how efficiently that radiation escaped from early galaxies. Young stars in galaxies are thought to have played a major role. Faint, low-mass galaxies may have been especially important because they were numerous, but the contribution depends on details that are difficult to measure, including how many ionizing photons their stars produced and what fraction could travel beyond the surrounding gas. Black holes may also have contributed in some places. The balance is still being refined. For most of human history, this era was beyond observation. Its light had traveled for more than 13 billion years, stretched by the expansion of space until much of what began at ultraviolet or visible wavelengths arrived in the infrared. That is one reason the James Webb Space Telescope was built to work so deeply in infrared light. Webb can examine galaxies from within the first several 100 million years after the Big Bang, not as reconstructed fossils nearby, but through light that actually left those systems when the universe was young. Spectroscopy allows astronomers to confirm distances, study emission from gas, estimate chemical enrichment, and test how rapidly stars were forming. The early universe, revealed by Webb, is busy. Astronomers have now spectroscopically confirmed a luminous galaxy seen only about 280 million years after the Big Bang. Observations this early are giving researchers a more detailed view of how rapidly the first galaxies assembled, how their stars affected surrounding hydrogen, and how quickly luminous structures emerged from the first gravitational foundations. The record keeps becoming more detailed. A galaxy seen at that distance is not a galaxy we are watching in the present. The photons entering a telescope detector now began their journey. Before the Sun existed, before the Milky Way had reached its present form, and before Earth had assembled, there is a generational thread hidden in that measurement. One generation of stars made elements for the next. One small galaxy merged into another. One region of ionized hydrogen joined a neighboring region. Layer after layer, cosmic history accumulated, without any observer being present to record it. Billions of years later, a telescope can collect a few of those traveling photons and recover part of the sequence. By then, the first stars themselves may be gone. Their individual names are unknown because they had none. But their influence remains in the chemistry of later stars, in the ionization history of intergalactic gas, and in the gradual appearance of galaxies where earlier there had been only dark matter and cooling hydrogen. This was the first great conversion in galactic history. Invisible gravitational structure became luminous structure. And once galaxies had learned, in a sense, how to turn incoming gas into stars, the next problem was how to keep that process going. A small early system could flare brightly for a time, but lasting growth required a continuing supply of matter from beyond its visible edge. The cosmic web had built the first foundations. Now it would begin feeding the galaxies themselves. A galaxy can only keep growing if matter continues to reach it. The first generations of stars may have transformed the chemistry of the young universe, but they did not provide an endless supply of fuel. Every star that formed removed some gas from immediate circulation. Every supernova disturbed the surrounding medium. If an early galaxy had been sealed off from everything around it, its bright period would eventually have been limited by whatever material happened to be inside at the beginning. Galaxies were never sealed systems. They remained embedded in the same cosmic web that helped create their dark matter halos. Long filaments carried ordinary matter through intergalactic space, and gravity continued drawing some of that material toward growing halos. The visible galaxy was only the innermost part of a much broader exchange. Before new gas could become part of a stellar disk, it had to cross an enormous surrounding region. Astronomers call this region the circumgalactic medium. The name sounds like a boundary, but there is no sharp edge. The circumgalactic medium, or CGM, is a diffuse mixture of gas extending far beyond the bright stars of a galaxy. Some of that gas is relatively cool, some is extremely hot. Some has arrived from the intergalactic environment with very little chemical enrichment. Other material has already passed through stars inside the galaxy, been enriched with heavier elements, and then thrown outward again. The galaxy is surrounded by its own history. Atoms in the circumgalactic medium may have traveled through several very different environments. One parcel of gas might have approached from a cosmic filament. Another might once have been inside the galactic disk before a group of supernovae pushed it outward. Some material can remain suspended in the halo for a long time. Some may later cool and return. This circulation makes the outer halo less like empty space and more like a reservoir with several currents flowing through it at once. Incoming gas encounters the gravitational field of the growing halo. As it falls inward, gravitational potential energy can be converted into motion and heat. In some halos, infalling material is strongly heated by shocks. Temperatures can become high enough for the gas to exist as a thin plasma was spread through a region much larger than the luminous galaxy. Hot gas does not automatically become star-forming gas. For it to move deeper inward, it often has to radiate away part of its energy. As the gas cools, thermal pressure becomes less capable of resisting gravity. Material can settle toward some regions where cooling may become more efficient and the next stage of galactic growth can begin. But settling inward does not mean falling directly toward the center. Matter, arriving at a galaxy, carries motion from the environment it came from. It may have been pulled along a filament. It may have interacted gravitationally with neighboring structures. The halo itself is not perfectly isolated or perfectly symmetrical, so the incoming gas almost always carries angular momentum. That small amount of sideways motion changes everything. As the gas moves inward, rotation becomes increasingly important. Material that cannot lose all of its angular momentum cannot simply drop into the center. Instead, it begins orbiting. Gas has another property that dark matter does not share in the standard cosmological picture. Gas can collide with gas. Two streams can meet, clouds can compress, turbulence can redistribute motion, radiation can carry energy away. Angular momentum can move from one part of the system to another. Through these interactions, a flattened rotating structure can gradually emerge. This is one of the major pathways by which galactic disks form. The contrast with dark matter is revealing. Dark matter contributes most of its influence through gravity. It does not appear to radiate energy through electromagnetic processes, so it cannot cool into a thin luminous layer in the same way ordinary gas can. Its distribution remains much broader. Inside that extended halo, ordinary matter can become concentrated into a disk only a fraction of the halo's total size. The two structures occupy the same galaxy but behave very differently. A mature spiral disk seen today can look precise from a distance. The early versions were often less orderly. Gas could arrive from changing directions. Dense clumps formed and moved through the disk. Star formation injected energy into the surrounding medium. Smaller galaxies disturbed the system as they passed nearby or merged with it. Rotation existed, but so did turbulence. A young disk could be thick and uneven. Its stars did not all occupy neat circular paths. Some regions might be forming stars intensely while others contained gas too warm or too diffuse to collapse. The geometry was continually being modified by whatever arrived next. Over time, some disks became more organized. The motions of younger stellar populations could remain concentrated near a relatively thin plane, while older stars or stars disturbed by earlier events occupied a thicker distribution above and below it. This is one reason a disk galaxy can contain both a thin disk and a thick disk, each carrying information about different parts of its history. Near the center, the structure can become denser still. Many disk galaxies contain a central bulge, a concentration of stars with orbital behavior different from the flat outer disk. Some bulges may preserve evidence of early rapid growth or mergers. Others can develop gradually as internal structures rearrange gas and stars. Farther outward lies another component that can be almost invisible in an ordinary image. The stellar halo contains sparse populations of old stars, globular clusters, and debris left behind by smaller galaxies that were disrupted. It is much fainter than the disk, Yet it can preserve a long record of earlier encounters, so even a galaxy that looks like one object is really several overlapping systems. A broad dark matter halo sets much of the gravitational environment. The circumgalactic medium stores and exchanges gas. A stellar halo carries remnants of previous mergers. A rotating disk contains much of the ongoing star formation. A central region records still other processes. None of these parts is completely independent. Gas moving through the halo can eventually feed the disk. Stars in the disk can return matter to interstellar space. Stellar winds and supernovae can push some of that material outward. A portion may escape the galaxy entirely. Another portion may remain bound and later fall back. Astronomers sometimes describe this returning motion as a galactic fountain. The scale is far beyond anything the word fountain usually suggests. Hot gas can rise thousands of light years above the disk before cooling enough to descend again. While it is outside the disk, it may mix with material that has never previously been part of the galaxy. What returns is not always chemically or thermally identical to what left. This continuous exchange makes galaxy growth less like filling a container and more like maintaining a circulation system. Matter arrives, some of it cools, some settles into the disk. A fraction becomes dense enough to form stars. Stars return energy and enriched material. Part of that material leaves the disk, some later comes back. Over billions of years, the same broad ingredients can move repeatedly between different states. Even the present Milky Way participates in exchanges of this kind. The night sky can make our galaxy feel complete because we see its stars already arranged around us. Yet beyond those stars is gas that belongs to a much larger ecosystem connecting the disk with the halo. The galaxy above and around you is not only the light that reaches your eyes. It also includes matter too diffuse to see without specialized instruments, material that may spend millions of years outside the star-forming disk before returning to it. And there is no guarantee that every returning parcel settles into the same aureole already present. Gas can arrive carrying angular momentum tilted relative to an existing disk. Satellite galaxies can disturb stellar orbits. Gravitational interactions can thicken a disk or warp its outer regions. Internal instabilities can move matter inward or outward. A disk can be damaged and later partly rebuilt. This is why disk formation should not be imagined as one completed event in the youth of a galaxy. It can continue, pause, reverse in places, and resume. A galaxy may spend billions of years adjusting to new material. The visible structure at any one moment is the current compromise between gravity, angular momentum, cooling, turbulence, star formation, and the accumulated disturbances of the past. Within the disk, the process becomes more concentrated. Gas that has traveled across intergalactic space and through a halo can eventually reach regions where temperatures are lower and densities are higher. Large molecular clouds form. Inside them, turbulence produces filaments and knots. Magnetic fields and gas pressure resist collapse in some places, while gravity gains the advantage in others. Only part of a galaxy's gas reaches this state. A galaxy may contain a large reservoir of material and still convert only a limited fraction into stars. Gas that is too warm does not collapse easily. Gas that is too diffuse may remain spread through the disk or halo. Turbulence can support a cloud against its own gravity. Magnetic fields can alter how collapse proceeds. Star formation requires particular local conditions. When those conditions are reached, dense regions contract. Smaller structures appear inside larger clouds. Protostars begin gathering material, and at that moment, the long journey of matter changes scale again. An atom that may once have moved through the intergalactic medium entered a dark matter halo, crossed the circumgalactic reservoir, cooled into a disk, and joined a molecular cloud can become part of a new star. The story of galaxy growth is written through journeys like this, repeated on scales too large and too numerous to follow one by one. And the stars created from that gas will not remain passive passengers. They will heat the medium around them, enrich it, stir it, and in some cases, blast material back toward the halo. The galaxy has learned how to build a disk. Now the disk begins learning how to regulate itself. Once a galaxy has gathered enough cold gas into its disk, the next stage is not simply to turn all of that gas into stars. Most of the gas does not collapse at once. Some remains too warm, some is too diffuse, some is stirred by turbulence. Magnetic fields thread through molecular clouds and can help resist collapse. Even within a cloud already cold enough to contain molecules, only certain regions become dense enough for gravity to take control. Star formation is selective. Inside a large molecular cloud, gas moves in complicated ways. Turbulence creates filaments, knots, sheets, and temporary concentrations. Some of these structures disperse again. Others collect more material. Where gravity becomes stronger than the combined support from pressure, motion, and magnetic effects, the gas begins contracting. Dense cores form. Within them, matter continues falling inward until a protostar appears. The process can sound like the final step in a long gravitational story, but it is actually the beginning of another cycle. A newly forming star starts influencing its surroundings almost immediately. Young stars release radiation. Some launch jets from their immediate environments. The most massive stars alter the surrounding gas far more strongly. Their ultraviolet radiation can ionize nearby hydrogen. Stellar winds carry material away from their surfaces at high speed. Cavities can be carved into molecular clouds. Dense material can be compressed along the edges of expanding bubbles, and after comparatively short lives, the most massive stars can explode. A supernova does not merely mark the death of one star. It injects energy, momentum, and newly produced elements into the interstellar medium. This is stellar feedback. The word feedback is useful because star formation changes the conditions that made star formation possible. Gravity tries to gather gas. New stars push back. Radiation heats the surroundings. Winds stir the cloud. Explosions can scatter material that might otherwise have collapsed into another generation of stars. A galaxy with plenty of gas can therefore form stars much more slowly than a simple inventory of its fuel might suggest. This regulation is important. Without it, dense gas could collapse too efficiently. A galaxy might convert a large fraction of its available material into stars very quickly. Instead, star formation often proceeds through an extended balance in which collapse and disruption occur together. The balance is not perfectly stable. A molecular cloud can spend part of its life assembling. Star fascinates begins in its densest regions. Massive young stars then disturb the same cloud. Some sections are dispersed, other sections may be compressed. Feedback can suppress collapse in one place, while helping to create favorable conditions somewhere else. A shock moving into nearby gas can raise its density. If that compressed region becomes sufficiently cold and massive, gravity may eventually take advantage of it. So the same star can participate in both interruption and continuation. Across a galactic disk, countless regions are going through different versions of this process. Some clouds are assembling, some are actively forming stars. Others are being broken apart by the stars they recently produced. The galaxy never needs to coordinate them. The overall rate of star formation emerges from the combined behavior of many local environments. This is one reason bright star-forming regions appear scattered through spiral galaxies rather than evenly distributed across the entire disk. Where gas becomes concentrated, conditions may favor collapse. Where recent generations of massive stars have heated or dispersed the material, star formation may temporarily decline. On larger scales, Observations show a broad connection between the amount of gas concentrated in a region and the rate at which stars form there. The relationship is not a simple rule governing every cloud, but the underlying tendency is clear enough. Denser reservoirs of suitable gas are generally able to support more star formation. Yet even this describes only part of the cycle. The stars themselves are changing what the gas is made of. The earliest cosmic gas consisted overwhelmingly of hydrogen and helium. By the time mature galaxies existed, generations of stars had transformed that chemistry. Inside stars, nuclear fusion builds new atomic nuclei. Different elements are produced through different stages and in different kinds of stars. Stellar winds return some of this material gradually. The late stages of lower mass stars release enriched outer layers. Massive stars can distribute additional material when they die. Explosive events contribute still more. Across billions of years, galaxies become chemically enriched. Astronomers use the word metals in a broad way for elements heavier than helium. In everyday chemistry, oxygen is not considered a metal. In astronomical language, oxygen contributes to metallicity, along with carbon, silicon, iron, and many other elements. That growing inventory changes the future of the galaxy. Gas containing heavier elements can cool differently from primordial gas. Dust grains become possible. Those grains can absorb and re-radiate energy, help shield molecules from some forms of radiation, and provide surfaces on which chemical reactions can occur. The raw material for later planetary systems also becomes increasingly diverse. Rocky worlds, elements that did not exist in meaningful abundance at the beginning of cosmic history. Silicon, magnesium, iron, oxygen, carbon, and many other ingredients had to pass through earlier generations of stars before they could become part of planets. A galactic disk is therefore a place where matter acquires history. A hydrogen atom may be nearly as old as the universe. An iron atom may have been assembled much later inside a star. A grain of dust may contain material that passed through more than one stellar generation before joining a new cloud. The next star forms from a mixture of old cosmic material and the products of stars that came before it. This recycling can continue for an immense span of time. Gas falls into a galaxy. Some becomes molecular. A fraction forms stars. Stars return part of their mass to the surrounding medium. That material mixes with gas already present and with fresh material arriving from outside. Later stars form from the new mixture. The chemistry of a galaxy, therefore, records parts of its past. Different stellar populations can carry different abundances of elements because they formed at different times or in different environments. A star preserves much of the chemical composition of the cloud from which it was born. Long after the cloud has vanished, remains. There is something strikingly durable about that. An individual star may move far from its birthplace. Its original neighbors may scatter through the disk. The molecular cloud that formed them may be destroyed within a relatively short astronomical interval. But the chemistry can still carry a trace of the environment that existed when the star began. Galactic history is not stored in one archive. It is distributed through motion, age, composition, structure, and light. And the same feedback that enriches a galaxy can also move matter far from the regions where stars form. When many massive stars and supernovae inject energy into a disk, hot gas can rise above and below the galactic plane. In a sufficiently massive galaxy, much of that material may remain gravitationally bound. It can expand into the halo, cool, mix with other gas, and eventually return. The journey may span thousands of light years. This is the galactic fountain at work again, but now the returning material has been chemically altered. A galaxy can send part of itself outward and later receive it back in a different state. In smaller galaxies, the consequences can be more severe. A dwarf galaxy has a shallower gravitational well. Gas accelerated by repeated supernovae can be more difficult to retain. Some material may escape into the surrounding environment rather than returning quickly to the star-forming regions. The same stellar feedback that regulates a large spiral can therefore reshape the future of a dwarf much more strongly. Size changes the outcome, so does environment, so does the amount of gas already present. Galaxies share the same basic physical ingredients, but their histories diverge because those ingredients are arranged under different conditions. Within a large rotating disk, another pattern begins to appear. Young stars are often concentrated along broad curved structures. Dust traces dark lanes. Clouds gather in certain regions. Blue-white stars illuminate parts of the disk with the brief brightness of youth. These are the spiral arms. They can look as though the galaxy has arranged its stars into permanent streams. But a spiral arm is not simply a fixed row of stars. The stars themselves orbit the galactic center. Gas moves. Different parts of the disk complete their orbits on different timescales. If the arms were made from exactly the same stars permanently locked together, differential rotation would gradually stretch and wind the pattern tighter and tighter. Real spiral structure is more complicated. In some galaxies, large-scale density patterns can help organize material into prominent arms. Stars and gas pass through regions where matter becomes somewhat more concentrated. Gas responds strongly because it can compress, collide, cool, and form new stars. The arm becomes bright partly because star formation is being enhanced there. The pattern can persist even while many of the individual stars that make it visible continue moving onward. One comparison is a region of congestion on a long road. Cars enter, they slow, they move through, then they leave. The pattern of congestion can remain even though the cars inside it keep changing. A spiral arm can work in a broadly similar way, although the physics is gravitational rather than mechanical traffic. But not every spiral galaxy follows one enduring density pattern. Some show many shorter, less organized arms. Local gravitational instabilities can create segments that appear, change, and fade. Interactions with neighboring galaxies can pull on a disk and strengthen a spiral pattern. Bars can rearrange orbits and redirect gas through the inner regions. Several mechanisms may contribute in the same galaxy. Our own Milky Way is part of this family. From inside its disk, we cannot see the entire structure from above. Astronomers reconstruct its shape indirectly by measuring stars, gas, distances, velocities, and radio emission across the galactic plane. What emerges is a barred spiral system whose form has changed over time and will continue changing. The band of the Milky Way visible from a dark place on Earth is therefore not a static architectural feature. It is a view from inside a moving disk. Stars are orbiting, clouds are assembling and dispersing, new suns are forming, older stars are returning material to space. Gas is arriving from the halo and being driven back toward it. Spiral patterns are being maintained, altered, or replaced. The galaxy is continuously rebuilding itself while appearing from one human lifetime to the next, almost unchanged. And internal processes can only reshape it so far. Eventually, another galaxy may pass close enough for its gravity to become part of the story. Then the architecture of the disk can change on a much larger scale. A galaxy does not have to touch another galaxy for the encounter to begin. Long before their stars overlap, their gravitational fields are already reaching across the space between them. Orbits shift. Outer gas is disturbed. Dark matter halos begin to pass through one another. The shapes of the galaxies may stretch slightly toward the approaching companion. Then, over hundreds of millions of years, the changes become easier to see. A close passage can pull stars and gas outward into long tidal tails. Material may form a bridge connecting the two systems. One side of a disk can become extended while another is compressed. Spiral arms can grow brighter or become distorted. The reason is that gravity does not act with exactly the same strength across an entire galaxy. The side nearest the companion feels a somewhat stronger pull than the far side. Across tens of thousands of light years, that difference matters. A star securely orbiting deep in the inner galaxy may remain there, while a star farther out can be shifted onto a much wider path. Gas responds even more strongly. Unlike stars, clouds of gas can collide. They can shock, compress, radiate energy, and lose part of their organized motion. During some encounters, large quantities of gas are driven into denser regions where star formation accelerates. This can create a starburst. For a comparatively brief period, a galaxy may produce stars far more rapidly than it did before the encounter. Dense young clusters appear. Massive stars flood their surroundings with ultraviolet radiation. Supernovae follow after several million years, sending energy back into the disturbed gas. The interaction can therefore trigger both the formation of stars and the processes that later limit that formation. Yet, even when two galaxies overlap almost completely, direct collisions between individual stars are rare. The distances between stars are simply too large. A galaxy can contain hundreds of billions of suns and still be mostly empty space. During a merger, one stellar population can pass through another, while only a tiny fraction of individual stars ever come close enough to collide physically. What changes their motion is the combined gravitational field. As two galaxies move through one another, that field can vary rapidly. Stars that once traveled on fairly organized paths may find themselves on new orbits. Some move farther outward. Some fall inward. Some become part of an extended halo. When the encounter involves two galaxies of similar mass, the transformation can be profound. Astronomers call this a major merger. If both galaxies began with stellar disks, the organized disk structure can be heavily disrupted. Repeated close passages redistribute orbital energy. Gas flows toward new regions. The central areas become denser. Eventually, after the galaxies have passed through one another several times, their cores can combine. The final system may look very different from either of its parents. A smooth elliptical galaxy can form under some merger conditions, with stars moving along a wide variety of orbits, rather than remaining concentrated in one thin rotating disk. The process that helps rearrange those orbits is sometimes described as violent relaxation. The name refers to rapid gravitational reorganization, not to stars smashing into one another. During the merger, the overall gravitational potential changes while stars are moving through it. A star can gain or lose orbital energy as the mass distribution shifts. Across a huge population of stars, the ordered motion of the original disks can become a much more mixed set of trajectories. Eventually, the remnants settle. From a distance, a mature elliptical galaxy may appear smoother than the spirals that existed before the merger. But that smoothness can hide a complicated past. Some of its stars may have formed in one galaxy, others may have formed in another. Still, others may have been created during the encounter itself. The outer regions can preserve shells, loops, and diffuse structures left by earlier passages. A calm appearance does not require a calm history. The outcome is different when one galaxy is much smaller than the other. This is a minor merge, and it is one of the most common ways large galaxies continue to grow. A small satellite can spend billions of years orbiting within the dark matter halo of a larger host. Each orbit carries it through a changing gravitational environment. Over time, the satellite can lose orbital energy through dynamical friction. As it moves through surrounding stars and dark matter, its gravity creates a slight overdensity behind it. That gravitational wake pulls back on the satellite and gradually alters its orbit. The process is slow. the satellite may complete many circuits before moving significantly closer to the central galaxy. But as the orbit shrinks, tidal forces become stronger. The outer dark matter halo of the satellite is often stripped first. It is loosely bound and extends well beyond the visible stars. Later, gas and stars can begin to escape as well. Those stars do not vanish. They continue along paths related to the orbit of the galaxy they once belonged to, forming long stellar streams around the larger host. Some streams can remain recognizable for an immense span of time. Others gradually disperse. Because the stripped stars have slightly different orbital energies, they move at slightly different rates. One group drifts ahead. Another falls behind. The structure stretches and becomes less distinct. Eventually, the stream can blend into the larger galaxy's stellar halo. The original satellite may no longer exist as a separate galaxy, yet its stars remain. This is one of the ways a large galaxy can carry the remains of smaller systems without displaying obvious signs of a recent collision. The Milky Way contains evidence of this process. Several stellar streams wrap through its halo. Some are associated with dwarf galaxies or star clusters that have been tidally disrupted. The Sagittarius dwarf galaxy provides one of the clearest examples. It has passed repeatedly through the Milky Way's gravitational field, losing stars that now form an extended stream around our galaxy. Those stars act like markers along an orbit. By measuring their positions, motions, and chemical compositions, astronomers can reconstruct parts of the encounter and learn about the gravitational field of the Milky Way itself. In this sense, destruction leaves information behind. The study of such remnants is part of galactic archaeology. Instead of excavating layers of rock, astronomers examine the ages, motions, and chemistry of stars. A star can retain a record of the material from which it formed. Groups of stars with related chemical patterns and related motion may reveal that they once belonged to the same smaller system, even after that system has been largely dispersed. Globular clusters can preserve similar clues. Some formed within their present host galaxies. Others appear to have arrived as part of smaller galaxies that were later absorbed. A compact star cluster can survive even when the larger system around it is stripped away. So the halo of a galaxy is not simply a sparse outer region. It can be a collection of memories. Each stream may represent an earlier satellite. Each unusual cluster may carry a different history. Each group of stars moving together may be a fragment of something that once had its own dark matter halo, its own gas, and perhaps its own generations of star formation. This gradual accumulation is central to the way large galaxies grow. The Milky Way was not assembled from one cloud in one event. Neither was Andromeda. Both contain stars formed in place and stars acquired from other systems. Their halos have been built in part from many separate histories, and the process continues. The large and small Magellanic Clouds are among the most prominent companions of the Milky Way. They interact with each other and with our galaxy. Gas associated with them stretches across the sky in a broad structure known as the Magellanic Stream. The large Magellanic Cloud is massive enough that its gravitational influence affects how astronomers model the Milky Way itself. These companions remind us that a galaxy is never entirely defined by its own visible disk. Its satellites matter, its neighbors matter, its place within a group matters. Far beyond the Milky Way, galaxy groups and clusters contain far more crowded environments. There, repeated encounters can reshape systems again and again. A galaxy may lose gas to its surroundings. A satellite may be stripped. Several galaxies may merge over time into one much larger central system. Some stars can even become detached from any single galaxy. In rich clusters, tidal interactions can scatter stars into the space between galaxies. These stars continue orbiting within the gravitational field of the cluster as a whole, producing a faint, diffuse glow known as intracluster light. It is starlight without one obvious galactic home. Those stars once belonged somewhere. They formed inside galaxies, moved with them, and were later removed by interactions across scales far larger than any planetary system. Now, they drift through the shared gravitational environment of a cluster. By this stage in the story, galaxies no longer look like isolated islands. They are more like temporary concentrations within a larger network of matter. Some are growing, some are being stripped, some are merging, some are losing companions that once seemed permanent. And deep inside many of the largest systems, another participant is responding to these changes. Gas, driven inward during interactions, can reach the central regions. Bars and gravitational disturbances can help remove angular momentum. Dense material can move closer to a supermassive black hole. The black hole itself may occupy only a tiny fraction of the galaxy's physical size. But when fresh matter begins falling toward it, the energy released can reach far beyond the center. A merger can rearrange a galaxy from the outside inward. What happens next begins near the center and can spread outward again. Near the center of a large galaxy, the scale of the story changes again. The galactic disk may stretch across tens of thousands of light years. The dark matter halo reaches much farther. Yet inside the innermost region, matter can begin gathering around an object so compact that its physical size is almost insignificant compared with the galaxy surrounding it. A supermassive black hole. Most large galaxies appear to contain one. Some hold black holes with masses equivalent to millions of suns. Others contain hundreds of millions or even billions of solar masses. Their presence is closely connected to the histories of the galaxies around them, although the relationship is not as simple as a black hole controlling every star from the center. Far from the nucleus, it does not. The orbit of a star in the outer galaxy is determined mainly by the combined gravitation influence of the galaxy's stars, gas, dark matter, and other mass. The black hole dominates gravity only within a comparatively small central region. Its broader influence comes from matter falling toward it. Gas approaching a black hole usually carries angular momentum. Instead of dropping directly inward, it begins orbiting and can form an accretion disk. As material moves through that disk, gravitational energy is converted into heat. The gas can become hot enough to produce intense radiation before it ever crosses the event horizon. The black hole itself does not shine. The surrounding material does. When the central region becomes luminous enough, astronomers call it an active galactic nucleus. In its most powerful forms, an active nucleus can become one of the brightest persistent sources in the universe. Some radiate strongly invisible light. Others produce ultraviolet radiation or X-rays. Some launch narrow jets of particles, moving at a substantial fraction of the speed of light. The energy can escape far beyond the small region where it originated. A jet may extend well outside the stellar body of its galaxy. Winds can push through surrounding gas. Radiation can heat material that might otherwise cool. This is where the central black hole becomes important to the life of the larger galaxy. Not because it reaches outward and directly commands the stars, but because it can alter the gas from which future stars would have formed. Gas is the vulnerable part of the system. Stars already formed can continue orbiting for billions of years, but future star formation depends on maintaining cold, dense reservoirs. If gas is heated, removed, stirred too strongly, or prevented from cooling, the supply available for new stars declines. An active nucleus can contribute to each of those processes. Fast winds from the central region can carry gas outward. Radiation can raise its temperature. Jets can inject energy into the hot atmosphere surrounding a massive galaxy or galaxy cluster. In some systems, jets carve large cavities into hot gas, The cavities can remain visible long after the particles that created them have moved on. The mechanical energy involved can help keep surrounding gas hot. That matters because massive galaxies often sit inside extended reservoirs of very hot plasma. Without continued heating, some of this gas could radiate energy away, cool, move inward, and eventually help replenish the cold material needed for star formation. A central black hole can interfere with that process. This is often called active galactic nucleus feedback. Feedback has become an important part of modern galaxy formation models because galaxies do not simply convert every available supply of gas into stars. Something regulates them. Stellar feedback does part of the work, especially in lower mass systems. In very massive galaxies, energy associated with central black holes appears to become particularly important. The exact mechanisms are still being studied. A simulation cannot easily follow every detail near a black hole while also representing an entire galaxy and its halo. The scales are too different. Processes near the accretion flow may unfold across distances tiny compared with the hundreds of thousands of light years over which their consequences eventually appear. So models must approximate some of the physics. Observations provide constraints, but real galaxies are complicated enough that more than one mechanism can operate at the same time. This makes quenching difficult to reduce to a single cause. A galaxy becomes quenched when its star formation drops and remains low. The word can sound final. In reality, the transition may be gradual, incomplete, or even temporarily reversible. A galaxy can experience a period of reduced star formation and later acquire new gas. Another may decline slowly over billions of years. A third may lose its cold gas comparatively quickly after entering a dense cluster environment. Different pathways lead toward the same broad result: fewer new stars. One pathway is exhaustion. If a galaxy keeps forming stars without receiving enough replacement gas, the amount of cold material eventually declines. Some of the gas becomes locked into long-lived stars. Some is returned later, some is expelled. But if replenishment falls behind consumption, the star-forming reservoir shrinks. Another pathway is heating. Gas can remain gravitationally bound to a galaxy while becoming too hot to collapse into molecular clouds. This is especially relevant in massive halos. As gas falls into a deep gravitational potential, it can be shock heated to high temperatures. If cooling becomes inefficient, the galaxy may contain enormous amounts of gas and still form relatively few stars. The problem is not always a lack of matter. Sometimes the matter is simply in the wrong physical state. A third pathway is removal. This becomes especially important in galaxy groups and clusters. A galaxy moving through the hot gas, filling a cluster, experiences pressure. The stars are largely unaffected because they are compact objects moving through enormous empty spaces. The galaxy's own diffuse gas is different. As the galaxy moves, external gas can push against its interstellar medium. If that pressure becomes strong enough, gas can be stripped from the galaxy. The process is known as ram pressure stripping. A spiral galaxy entering a rich cluster can therefore lose part of the material it needs for future star formation without losing most of its stars. From a distance, the stellar disk may remain recognizable, but its fuel supply is being altered. The outer regions can stop forming stars first. Over time, the galaxy may become progressively more passive. There is another environmental process that works more indirectly. A galaxy can lose access to the larger reservoir of gas surrounding it. If the circumgalactic supply is removed or prevented from reaching the disk, the galaxy may continue forming stars for a while, using whatever cold gas remains inside, but the reservoir is no longer being replenished. Astronomers sometimes call this starvation or strangulation. The language sounds severe, but the physical change can be gradual. A galaxy simply stops receiving enough fresh material. The disk continues using what it has. Then the supply diminishes. The rate of star formation falls. In crowded environments, repeated gravitational encounters can also disturb galaxies. Some interactions drive gas inward. Others strip material outward. A disk can be heated dynamically, making stellar orbits less orderly. Spiral patterns can weaken. A system that once looked like a blue star-forming spiral can become smoother and redder without requiring one single catastrophic merger. This is one reason morphology and star formation history do not map perfectly onto each other. A spiral shape does not guarantee vigorous star formation. An elliptical shape does not tell the complete story of how star formation stopped. Galaxies carry overlapping histories: internal structure, environment, halo mass, black hole activity, gas supply, past mergers. All of them matter. The transition becomes visible in the stellar population. Massive blue stars live relatively short lives. If a galaxy stops forming new stars, those bright young stars disappear from the population first. Longer-lived, lower-mass stars remain. The integrated light of the galaxy becomes dominated by older, redder, stellar populations. The change in color is not because the entire galaxy suddenly cools. It is because the short-lived blue stars are no longer being replaced. A quenched galaxy can therefore remain bright for an almost incomprehensible length of time. Billions of stars continue burning. Red giants still appear. White dwarfs accumulate. Binary systems continue orbiting. Occasional supernovae may still occur from older stellar populations. The central black hole remains. The dark matter halo remains. The galaxy is not empty. It is simply making fewer new stars. This is the strange meaning of a dead galaxy. It is full of living stars. The word describes a change in production, not an absence of light. There is a useful human-scale way to think about that difference. A city seen late at night may still contain millions of people, buildings, roads, and lights, even if construction has nearly stopped. The city has not disappeared. Its existing structure remains. A quenched galaxy is similar, only in this limited sense. Its stellar population continues, while the rate at which new stellar generations are added becomes low. But galaxies can move between states. Some passive galaxies still contain traces of cold gas. Some show small episodes of renewed star formation. After receiving fresh material, a merger can bring gas. A cooling episode can restore part of the supply. Even a system that has spent a long period in relative inactivity is not guaranteed to remain unchanged forever. Cosmic evolution resists clean endings. The broad statistical patterns are clear, but individual galaxies often carry exceptions. And this is especially true when astronomers compare galaxies across different environments. In the field, far from rich clusters, a galaxy may retain its gas supply for a long time. Inside a dense cluster, interactions with the surrounding medium can transform it more rapidly. Near the center of a massive group, repeated mergers can build a large elliptical galaxy whose stars are old even while the galaxy itself continues gaining mass. This creates one of the more subtle distinctions in galactic evolution. A galaxy can continue growing after it has mostly stopped making stars. It can acquire stars that were formed elsewhere. A dry merger is one example. When two galaxies containing little cold gas combine, the encounter may produce relatively little new star formation. Instead, the remnant simply inherits the existing stars of both systems. Its mass increases. Its size can increase. Its stellar population remains old. Growth continues without much renewal. This is common in the histories of some of the largest galaxies. A giant elliptical near the center of a cluster may have formed many of its stars early, then spent billions of years adding stars through mergers. In that sense, there are at least two different clocks running inside a galaxy. One tracks when its stars were born, another tracks when the galaxy itself was assembled into its present form. those clocks do not always agree. An enormous galaxy observed today may contain stars that are mostly very old, even if much of its final size was assembled later through mergers. That distinction has helped reshape the old picture of galaxies as objects moving neatly from youth to maturity to old age. There is no single path. There is only a network of possible histories constrained by physics. Gravity builds, gas cools. Stars form, feedback pushes back, environment removes, mergers rearrange. Black holes alter the thermal balance, and over enough time, many galaxies settle into states where star formation becomes less important than the slow evolution of the stars already present. The largest changes can therefore become difficult to see. A galaxy may look tranquil precisely because the processes that once made it active have become less effective. The bright blue regions fade, dust lanes become less prominent, cold clouds grow scarce, the light becomes smoother, and underneath that smoothness lies the complete record of how the galaxy arrived there. For billions of years, matter entered, circulated, cooled, formed stars, was expelled, returned, and was rearranged. Then the balance shifted. Less cold gas reached the places where stars could form. The galaxy continued shining, but the cycle weakened. There is one final scale on which to follow this story. Not one galaxy alone, not even a cluster, but the future of familiar galaxies over the immense stretch of time still ahead. The Milky Way and Andromeda are already moving within the same local gravitational environment. Each has spent billions of years assembling itself from smaller systems. Each contains a central black hole, stellar halo, satellite population, dark matter halo, and a long record of accretion and merger. Their present shapes are temporary. Given enough cosmic time, gravity will change them again. The future of the Milky Way is already visible as a faint patch in the northern sky. Under dark conditions, Andromeda can be seen without a telescope. It does not look like another galaxy in the everyday sense. To the eye, it is only a small, pale blur, easy to miss beside brighter stars. Yet that blur is the combined light of an enormous stellar system, roughly 2.5 million light-years away. Andromeda and the Milky Way are the two dominant large galaxies of the local group. Between and around them are many smaller companions, including the Triangulum Galaxy, the large as small Magellanic Clouds, and numerous dwarf galaxies. All of these systems participate in the same local gravitational environment. For many years, one particular future was described with unusual confidence. Andromeda is approaching the Milky Way along our line of sight, and older models indicated that the two large spirals would make a close passage several billion years from now, then lose orbital energy and eventually merge. Illustrations often showed the night sky filling with Andromeda before both disks were stretched into long arcs of stars. That future is still possible, but it is no longer useful to describe it as inevitable. The difficulty is sideways motion. Knowing that Andromeda is moving toward us is not enough to determine where it will be billions of years from now. A small tangential velocity across the sky can become a very large displacement over such a long interval. The masses of the Milky Way and Andromeda matter as well, especially the masses of their extended dark matter, halos, and the two galaxies are not alone. The Triangulum Galaxy pulls on Andromeda. The large Magellanic Cloud pulls on the Milky Way strongly enough that it changes how the motion of our galaxy is modeled. Each of these influences alters the future orbit by a small amount, and small differences accumulated over billions of years can lead to very different encounters. A study published in 2025 explored many possible local group futures using measurements from Hubble and Gaia. Once the uncertainties in the motions and masses of the major galaxies were included, the chance of the Milky Way and Andromeda avoiding a merger during the next 10 billion years came out close to 1/2. Then the calculation shifted again. A 2026 preprint using newer Gaia-based proper motion estimates, found a much higher merger probability in its preferred model, while also showing that the answer remained highly sensitive to the adopted sideways motion of Andromeda. The authors concluded that present measurements still do not fix one secure outcome. That changing forecast is not a weakness in the science. It is a demonstration of what long-range prediction means in a many-body gravitational system. Better measurements alter the starting conditions. Different estimates of mass or motion produce different paths. The physics remains the same, while the possible histories narrow or widen as the data improve. So there is no single picture of the local group's future that must occur. The Milky Way and Andromeda may eventually merge. They may pass at a greater distance and remain separate for much longer. They may experience a close encounter that changes both systems without producing an immediate final union. And if a merger does happen, it would unfold much more gradually than the word collision suggests. The dark matter halos would begin interacting first, long before the bright stellar disks overlapped. Tidal gravity would distort the outskirts. Spiral structures could be stretched. Some stars would be moved onto wider orbits. Streams and bridges could form between the galaxies. Then the disks could pass through one another. Even in that overlap, direct collisions between individual stars would remain very unlikely. The distances separating stars are too large. Most would continue moving through the changing gravitational field, although their orbits could be rearranged dramatically. Gas would respond differently. Interstellar clouds could collide and compress. Some gas might lose angular momentum and move toward the central regions. If enough cold material remained in the two galaxies, the encounter could temporarily increase star formation. But the galaxies several billion years from now will not contain exactly the same gas reservoirs they contain today. So the strength of any future starburst cannot be assumed in advance. After a close passage, the galaxies might separate again. Gravity could draw them back. Dynamical friction could gradually remove orbital energy. A sequence of encounters might continue until the two systems became one larger gravitational structure. The familiar spiral patterns would not survive unchanged. Stars from both galaxies would become mixed into a new distribution. The remnant might become smoother and more elliptical, or it might develop another form depending on how much gas remained and how the encounter unfolded. Near the center, another merger could begin on a much smaller physical scale. The Milky Way contains Sagittarius, a star, a black hole of about 4 million solar masses. Andromeda contains a much more massive central black hole. If their host galaxies eventually merged, the black holes would not immediately meet. Each would first travel with the dense central region of its original galaxy. Only after the galactic cores came together would the black holes begin a longer inward migration. They could eventually become gravitationally bound to one another. Interactions with surrounding stars and gas could continue reducing their separate. At the final stage, if they coalesced, the system would release energy through gravitational waves. By then, the original spiral galaxies would be memories preserved only in the motions and chemistry of their stars. But there is another possibility worth keeping beside this one. Perhaps the Milky Way and Andromeda do not merge within the next 10 billion years. The future would still not be static. The Large Magellanic Cloud is already influencing the Milky Way. The Sagittarius dwarf is already being disrupted. Smaller satellites continue orbiting, losing material and responding to the changing gravitational field. Andromeda has its own population of satellites and its own record of earlier accretion. The local group will keep evolving regardless of whether its two largest spirals ultimately become one. From the present moment, Andromeda offers an unusual view of that uncertainty. The light visible tonight began crossing intergalactic space about 2.5 million years ago. It shows Andromeda long before any of the predicted future encounters. The galaxy we see is already an old image of a system that has continued changing while its light traveled toward us. And from Andromeda, the Milky Way would also be seen in the past. Neither galaxy can observe the other as it is now. Gravity, however, responds to the systems occupying the same present universe. Their halos, satellites, and neighboring galaxies continue shaping trajectories that no distant observer can yet watch to completion. This is the scale on which a galaxy's apparent permanence finally dissolves. The Milky Way has had many earlier forms. It will have later ones. Its spiral arms are not permanent markings. Its satellite system is not fixed. Its stellar halo is still absorbing the remains of older structures. Even the relationship between our galaxy and its largest neighbor cannot yet be reduced to one guaranteed ending. For billions of years, galaxies have been growing through uncertainty of this kind. Every merger depended on an orbit. Every surviving satellite passed through a history in which another trajectory was possible. Every present-day galaxy is one realized path through an enormous landscape of gravitational interactions. And whatever happens between the Milky Way and Andromeda, their future will continue the same process that built them. Stars will move, gas will be gained or lost, smaller systems will be reshaped, old structures will fade into new ones, and beyond the local group, the universe itself will keep expanding, gradually changing which galaxies can remain part of one another's observable sky. That longer fading belongs to the final part of the journey. Galaxies do not end with a single event. There is no final explosion that announces the close of their story. No moment when the last spiral arm vanishes and the entire system becomes dark. The fading happens through many smaller changes spread across timescales so long that no civilization could watch the whole sequence unfold. A galaxy first becomes quieter because its supply of cold gas changes. Some of that gas is turned into stars, some is heated, some is pushed outward, some remains in the halo, but can no longer cool efficiently enough to return to the star-forming disk. New material from outside may become harder to acquire. The balance gradually shifts. The bright, short-lived stars disappear first. Massive blue stars survive for only a small fraction of a galaxy's lifetime. Once star formation declines, they are no longer continually replaced. Their brilliant light fades from the overall population, leaving longer-lived stars to dominate the galaxy. The transformation can make a galaxy appear redder and smoother. But beneath that changing light, stars continue moving. A passive galaxy can still contain billions or trillions of them. Some remain on orderly orbits. Others follow the more scattered paths created by ancient mergers. Stellar remnants accumulate. Binary systems continue their long interactions. Nothing has stopped. The pace has simply changed. On far longer timescales, even the remaining stars begin to age. Stars, similar to the Sun, eventually exhaust the hydrogen in their cores, expand through later stages, and leave behind white dwarfs. More massive stars may end as neutron stars or black holes. Lower mass red dwarfs can continue shining for far longer than the present age of the universe. As the brightest stellar populations disappear, galaxies become progressively dimmer. The visible structure that once defined them begins to lose contrast. A spiral arm is easy to see when it contains luminous young stars and dark lanes of cold dust. When star formation becomes rare, that pattern becomes less obvious. The gravitational structure may remain for a time, but the bright traces that made it easy to recognize are gone. Eventually, a galaxy's identity becomes less about where new stars are being made and more about the motions of old stars and remnants. The same is true on larger scales. Galaxy groups can continue to evolve through mergers. systems that remain gravitationally bound may slowly combine. In dense environments, the number of separate galaxies can decrease as large central systems accumulate stars from smaller companions. The local group itself is one such bound environment. Whatever path the Milky Way and Andromeda eventually follow, the galaxies near us are not isolated from one another. Their long-term future will be shaped by mutual gravity, satellite interactions, and the slow rearrangement of matter inside the group. Far beyond the local group, however, another process has been unfolding for billions of years. The expansion of the universe is accelerating. On very large scales, distant galaxy groups and clusters are being carried apart as space expands between them. Regions that are not gravitationally bound to one another will continue separating. Over enough time, many galaxies that can be observed from the present-day universe will become increasingly distant. Their light will be stretched to longer wavelengths. They will become fainter, and eventually some will pass beyond the distance from which newly emitted light can ever reach observers who remain within our gravitationally bound region. The universe seen from the far future would therefore look less crowded than the universe seen today. Not because all of those distant galaxies had vanished, but because cosmic expansion would have carried them beyond observational reach. A future observer inside the remnant of the local group might see only the stars and remnants belonging to the local gravitational system. The great cosmic web would no longer be easy to reconstruct from nearby observations. Clusters now visible across billions of light years would be absent from the accessible sky. The broader universe would still exist beyond the horizon, but its light would no longer arrive. Inside the remaining bound system, stellar evolution would continue. One generation after another would end. Gas returned by dying stars could occasionally provide material for limited new star formation, but the amount of easily available fuel would continue declining. The universe would become increasingly dominated by long-lived low-mass stars and stellar remnants. White dwarfs would accumulate, neutron stars and black holes would remain. Planetary systems around surviving stars would continue orbiting through an environment increasingly different from the bright universe of the present. And yet this distant future is not the main reason galaxies matter. Their history is already contained in everything around us now. The atoms in Earth were processed through earlier generations of stars. The sun formed inside a galaxy that had already spent billions of years gathering gas, enriching itself, absorbing smaller systems, and rearranging its structure. The elements in rock, water, atmosphere, and living cells are connected to that history. A galaxy is not only a container for stars, it is an environment in which matter is repeatedly transformed. Gravity collects material, stars alter it, explosions return it, clouds mix it, later stars inherit it, planets emerge from it. The cycle continues until the conditions that once supported frequent star formation gradually disappear. Seen from this perspective, a galaxy's long life is not defined by any one shape. The first galaxies did not look like the Milky Way. The Milky Way itself has not always looked as it does now. Future galaxies will not preserve the forms we recognize today. What persists is the underlying sequence of transformation. Tiny density variations grow under gravity. Dark matter gathers into halos. Gas falls inward. Heavy elements spread. Disks form. Spiral patterns emerge. Satellites are captured. Mergers rearrange stellar orbits. Central black holes influence the surrounding gas. Star formation slows. Old stars remain. Then those stars begin, one by one, to leave the main sequence. Across the entire history, there is no requirement that a galaxy remain recognizable. The universe keeps working with the same matter, in different arrangements. A star that once belonged to a dwarf galaxy can later orbit in the halo of a larger one. Gas expelled from a disk can cool and return. A cluster of stars can survive after its original galaxy has disappeared. A galaxy can grow larger even after most of its own star formation has stopped. The boundaries are temporary. The materials keep moving. Tonight, the Milky Way still contains cold clouds where new stars are forming. Young stellar groups are still emerging. Old satellites are still being stretched. Gas still moves through the halo. And far beyond our own galaxy, other systems are passing through different stages of the same long history. Some are forming stars rapidly, some are merging, some have already become passive. Some are only now being seen through light that left them when the universe was young. Each one occupies a different moment in a process that began with tiny variations in the early cosmos. The photographs make them look still. Gravity tells a different story, and somewhere inside the fading light of every galaxy, the old stars keep their orbits,